Okay. That's good. Done. Okay. Hi, I'm Robert Rand, and I'll be talking about verifying probabilistic programs in the presence of an adversary. And basically, what we're trying to explore is the relationship between non-determinism and probability in a program. And we're going to express non-determinism through the common notion of an adversary. We're not going to know exactly state what the adversary's goals are, but we're going to be more focused on what the adversary's powers are. And I'll get to that in more detail. We're going to try to understand these through both the lenses of program equivalences, so what program equivalences hold in various models, because notoriously probability and non-determinism together will break some common program equivalences. And we're also going to try to look at these through the lens of verification, specifically what kind of core logic rules can be proved about the various models. So let's look at this program. First, we're going to toss a coin, and it's going to land heads with probability 1/2, heads corresponding to true. Then if it landed heads, we're going to toss it again, now with a 1/3 probability of landing true. So if you look at this program that this tree that you see on the screen, it represents a distribution. And the left side is where we threw 2 heads in a row, and you can figure out what the other 3 branches are. So they each have a probability associated with them, which you get by multiplying down. So what happens, hopefully you can see the bottom of the screen, when then there's an adversary who is going to choose, denoted by this or-like symbol, between assigning x to 1 and assigning x to 2. How does that transform the distribution that we're looking at? Well, firstly, we have to specify how strong is the adversary. So what I've got here is 5 levels of possible adversary strength, sort of in increasing order, and I'll explain to these as we go through them. So first, let's consider the simplest possible adversary, which is an adversary who only knows the program but doesn't actually know the content, doesn't know the execution itself. So this adversary basically has to choose beforehand whether he is going to update x to 1 or 2, and that's going to happen throughout the distributions. So we're either going to get this or we're going to get the identical thing with x being 1 throughout the distribution. Interestingly, this simple model breaks a classic program equivalence, which is if B, then C, else C should be identical to just running C. But it isn't in this case, because by branching on B, we know that in the first case B was true, and in the second case B was false. So the adversary could actually choose different paths in those 2 commands represented by C, assuming that there is some non-determinism going on there. That is, he gets a choice there. So what if we actually explicitly gave that power to the adversary? So the adversary knows how B landed. Well, suddenly there's a far wider range of possible distributions we can arrive in. And this is an example of one of them. So the adversary is going to assign x to 1 if and only if the coin flip landed heads. So suddenly we get, there's a grand total of 4 now possible distributions we could be in, depending on how the adversary wants to react to the coin toss. This also breaks a pretty classic program equivalence, which is you would expect that since x and y these 2 commands don't reference each other, their order doesn't matter. But it matters very much, because in the first example, the adversary can react to the coin toss. So if the adversary, just as an example, wanted to ensure that x or y is equal to 1, he can do that in the first example, whereas in the second example, he can't do that with probability more than half. But we're still limiting the adversary there. The adversary knows only current stuff in the program, but doesn't actually have access to the program trace, which is equivalent to seeing this distribution tree up and down. Well, what if he does? Suddenly we have even more possibilities, because even though those 2 right branches of the program are indistinguishable to us, or are indistinguishable in terms of the program state, they are distinguished by the trace that led to them, and the adversary can update in one of those cases and not update in the other. And this breaks an even more basic program equivalence, because we're tossing a coin and then we're overwriting the result. And that should obviously, in almost any programming language, that's the same as not having tossed the coin to begin with. But when we tossed a coin, we basically gave the adversary something to react to in his later choices. So these aren't equivalent at all. Finally, we might be interested in a case where the adversary can actually know the results of the entire program execution. So here I'm assuming that later in the program, the adversary is going to toss a coin, which is going to land heads with probability 3/5. The adversary can respond to that coin toss that will happen later by assigning x to 1 if it lands true and x to 2 if it lands false in the future. And that, of course, makes these programs much more difficult to verify. It means that this adversary is very powerful. And again, it breaks classic program equivalences. So here, suddenly the order of assigning x and y really matters, because if the adversary can choose between the two of those, he knows what the random bits look like. He can choose the one that gives him the result he wants. So if he wants y to land heads, he has, instead of 1/2, he has 3/4 chance that he can actually do that. That's in the case where there's a single stream of random bits. There's also a slightly different variant where every command has an associated set of random bits, and the adversary knows them beforehand. In that case, we don't even have this, that a non-deterministic choice between C and C itself should be just equivalent to running C, because the adversary can again choose whichever one of those two commands is beneficial to him. So hopefully that gives you a sense of these 4 or 5 possible ways that non-determinism and probability can interact with each other. It's also interesting to explore what we can verify about these kinds of programs. So as you might expect, the first one, where the adversary has very little knowledge, is the easiest to verify. And it has this very simple rule, which you could have for a standard non-probabilistic language as well. I'll give you a quick example of this. Let's zoom in a bit. Let's say C1 is assigning x to 1 and C2 assigns x to 2. Well, obviously, we can conclude from each of those that the probability of x being 1 in the first case is 1. And likewise, that's the probability of x being 2. And then, in this simplest model, we can then say either x is equal to 1 with probability 1, that means throughout the distribution, or x is equal to 2. That isn't true, however, if we go to our other models. And here you might note that the second and third are grouped together, and that's because Hoare logic doesn't really know about history. It only knows about program state. So there might have been an arbitrary amount of assignments to identifiers we don't know about in a program. So that exact Hoare triple that I showed you before isn't valid at all here, and that's because of the tree I showed you earlier. Even though the adversary is choosing between one of the two commands, he can choose it based on an earlier coin flip. So there may be some probability that is not 0 or 1 of x being assigned to 1. And we obviously have a rule for these even harder cases, and it's unfortunately the rule that you might expect we would get, which is we can do only deterministic reasoning about the program. So in other words, we can't say the probability is going to be 1/2 ever. In these kinds of programs where the adversary makes a choice, we're going to have to basically say, we can only have things of the form probability of something equals 1, which is the same as just saying something equals 1. So that's it. Hopefully that gives you a general sense of how probability and non-determinism can interact in sort of a whole variety of models, and how all this depends on exactly what information we choose to give the adversary who is working against us. Thank you.
Yeah, it's very interesting. So I have 2 questions. One is, you mentioned that on the previous slide when you had discussing 2 and 3 that Hoare logic doesn't let you talk about the history. But that's not true once you add ghost state or auxiliary state, which is typically used precisely in order to track the history. So I'm wondering if that means your logic is not sound in the presence of ghost state.
Well, it doesn't mean it's not sound, because what I was actually saying, what I was saying here was that since we don't know history, the second rule, we need a more restrictive rule for this second case. Like I might ideally, if I kind of could track the entire history and say, there has never been a coin tossed, then I would be able to safely use the original Hoare logic rule. Since I was saying in general Hoare logic, we don't have the ability to say no coin has ever been tossed, or there is no probabilistic value sitting here for us to use, I have to use this restrictive rule. So this rule is, and that's, interesting. I'd be interested in pursuing whether we could have a more general rule, a more usable rule, if we have this auxiliary state.
Okay, but so if you added auxiliary state, would you then have to distinguish between 2 and 3?
No, I wouldn't. It's possible that I would be able to make a rule that is more general for 2.
I see.
But this rule would still be valid.
Okay. And my second question was, don't take this the wrong way, but what is the relation to functional programming?
That's a good question. So a whole bunch of this, I was looking at sort of, how we can apply this to, there's a probability monad and such. And a lot of the ideas here, I think, carry through to functional programming. This was, is certainly, not a purely functional program, but I think that the ideas of integrating probability and non-determinism are important enough to the functional programming community that it was worthwhile to, bring this up here.
Okay, thanks.
But thanks for asking.
Hi. Do you know if it's possible to characterize the different adversaries in terms of algebraic effects and equations?
I'm fairly certain that this could be done. I mean, there's a ton of literature on, I think, the algebraic effects, character, and non-determinism and probability. There's a wealth of research that's been done in sort of trying to understand, characterize precisely probability through power domains and through a whole bunch of different more abstract mathematical frameworks. I was interested in sort of simplifying things in terms of just understanding these through, operational semantics and then stuff that we were able to prove directly from the operational semantics we're specifying. But I think that's a worth investigating.
There's recent work on making things like Hoare logic from specifications of algebraic effects, and I wonder if you'd possibly get the same rules you have here for the different characterizations. It'd be interesting to see.
Oh yeah, definitely.